August 17, 1943. Schweinfurt, Germany. The wreckage still smoldered when they arrived. Oberfeldwebel Klaus Richter stepped through twisted aluminum, his boots crunching on shattered perspex. Another B-17 Flying Fortress down. The 43rd this month. But this one landed almost intact in a farmer's field, belly up like a dying whale. Richter had torn apart dozens of American bombers. He knew every rivet, every wire, every weakness. The Reich depended on men like him to understand the enemy's machines, to find vulnerabilities, to turn American engineering against itself. But when his team cut into the fuselage that afternoon, everything changed. The armor plating protecting the cockpit wasn't steel. It wasn't aluminum alloy. Under the cutting torch's flame, it behaved differently, lighter, stronger, stranger. Richter ran his gloved hand across the surface. Smooth. Almost like glass, but it had stopped a 20mm cannon shell. The round was still embedded, mushroomed but not penetrated. His assistant, Werner, held up another piece. Herr Oberfeldwebel, this weighs nothing. How can this stop bullets? Richter didn't answer. He was staring at the material's cross-section. Layers. Hundreds of thin layers pressed together, each one thinner than paper. Not metal. Not ceramic. Something organic. Something that shouldn't exist in a warplane at 25,000 feet, in temperatures that froze oil solid and turned men's breath to ice. Package everything, Richter ordered. Label it classified. Berlin needs to see this immediately. The Americans had changed the game. And Germany was already behind. 6 months earlier, Luftwaffe intelligence officers sat in a bunker beneath Berlin, reviewing combat reports with growing alarm. The numbers were devastating. B-17 formations were penetrating deeper into German airspace, shrugging off fighter attacks that would have destroyed any other bomber. Feldmarschall Erhard Milch slammed his fist on the table. Gentlemen, we are losing this war in the air. These American bombers are bleeding us dry. The statistics painted a grim picture. Each B-17 shot down cost Germany an average of 3 fighters and 2 pilots. The bombers flew in tight formations, their overlapping .50 caliber machine gun fields creating a wall of lead. The Americans called it mutual support. The Germans called it a meat grinder. Test pilot Hans Fay had fired 200 rounds into AB-17's tail section during a capture evaluation. The bomber absorbed the damage, kept flying, and returned to England. It's not just armor, Fay explained to the assembled officers. It's redundancy. 4 engines when they need 2. Self-sealing fuel tanks. Crew positions with overlapping responsibilities. And armor that's lighter than ours but somehow more effective. He showed them photographs taken from gun camera footage. Direct hits that should have crippled the aircraft resulted in minor damage. Find out how they do it, Milch ordered. Strip every captured bomber down to the frame. The Führer wants answers, not excuses. The race to understand American aviation technology became Germany's most urgent technical priority. Every downed B-17 was a treasure trove of intelligence. But most crashed in flames or fell into the English Channel. The Schweinfurt bomber would be different. It would reveal a secret America had hidden in plain sight. The package arrived at the Luftwaffe's Technical Research Center in Rechlin 3 days later. Professor Heinrich Vollmer, the Reich's foremost materials expert, carefully unwrapped the armor samples under laboratory lighting. His hands trembled slightly, not from age, but anticipation. For 2 years, he'd been trying to solve the B-17 problem. German bombers required heavy steel armor that reduced payload and range. The Americans somehow protected their crews without the weight penalty. Vollmer placed a sample under the microscope. His breath caught. The material consisted of thousands of individual layers, each one a woven fabric, pressed together with resin under enormous pressure. The fibers weren't cotton. They weren't silk. Under polarized light, they showed a crystalline structure he'd never seen in organic materials. Tensile strength tests shocked him further. The material withstood forces that would snap steel cables of equivalent weight. When struck by projectiles, it didn't crack like ceramic or tear like metal. It delaminate, spreading impact energy across hundreds of layers. "This is ballistic fabric," Vollmer whispered to his assistant. But the Americans don't have access to synthetic fibers advanced enough for this. Neither do we. He ran another test, heating a small sample. At 300 degrees Celsius, it barely degraded. Steel weakened at such temperatures. Aluminum melted. Vollmer worked through the night, documenting everything. By dawn, he had his conclusion. The Americans had developed a revolutionary composite armor, lighter, stronger, and more heat-resistant than anything in the German arsenal. His report to Berlin was brief: "We are technologically outmatched. Recommend immediate priority development program." But Vollmer had missed something crucial. The material's true origin wasn't in any American laboratory. It came from nature itself, refined and weaponized in ways that would change warfare forever. October 1940. Wright Field, Dayton, Ohio. Colonel Curtis LeMay didn't believe it at first. A civilian engineer named George Stout stood in his office, holding what looked like a thick piece of cardboard. "Colonel, this will stop a .30 caliber round at point-blank range and weighs 1/10 what steel armor weighs." LeMay, a man who trusted numbers more than promises, ordered an immediate field test. They mounted the material on a test frame and fired a Springfield rifle at it from 20 feet. The bullet penetrated the first few layers, then stopped cold, embedded in the composite structure. LeMay examined the entry hole. Minimal deformation. No spalling. No secondary fragmentation that would injure crew members. He looked at Stout. "What is this made of?" "Phenolic resin and cotton fabric, sir. We're calling it composite armor. The concept is simple: disperse impact energy across multiple layers rather than trying to stop it with a single thick plate. Each fabric layer is impregnated with resin, then compressed under extreme heat and pressure. The result is lighter, cheaper, and more effective than steel." LeMay ran the calculations in his head. AB-17 carried 450 pounds of armor protecting crew positions. Replacing it with composite material would save 350 pounds, enough for additional ammunition or fuel. But there was a bigger prize. Lighter armor meant heavier bomb loads. Heavier bomb loads meant more German factories destroyed per mission. "Put it in production," LeMay ordered. "I want every B-17 rolling off the line equipped with this. And make it classified. If the Germans figure out how simple this is, they'll copy it in a month." Stout nodded. "We've already started, sir. We're calling the specific variant for aircraft armor Doran. It's a trade name, but it'll stick. America's secret weapon wasn't a bomb or a gun. It was engineering pragmatism, taking simple materials and combining them in ways no one else had considered." By mid-1943, every B-17G model left Boeing's Seattle plant with Doran composite armor protecting vital crew stations. Pilots loved it. The armor panels behind their seats were 2 inches thick but weighed less than their parachutes. More importantly, they worked. Combat reports documented dozens of incidents where composite armor stopped cannon shells and shell fragments that would have killed unprotected crew members. But keeping the secret proved harder than developing the technology. German intelligence knew the B-17s had improved armor. What they didn't know was the material's composition. Captured American airmen were interrogated extensively, but most crew members never saw the armor. It was installed during manufacturing, hidden behind interior panels and equipment racks. The few who did see it described it as thick cardboard or some kind of plastic, descriptions that led German analysts down false paths. Technical Officer Werner Lucht spent 6 months investigating American plastic manufacturing capabilities, convinced the armor was an advanced synthetic polymer. His reports to Berlin emphasized the need for Germany to expand its chemical industry. Meanwhile, the actual material sat in Vollmer's laboratory, its true nature still partially mysterious. The breakthrough came from an unexpected source. A Luftwaffe pilot named Karl Schroeder was shot down over England and captured. During his processing at an RAF interrogation center, he noticed something odd: the British weren't using composite armor in their bombers. He asked a guard about it during a cigarette break. The guard, tired and talkative, shrugged. "The Yanks have that fancy layered stuff. We're still using steel like proper engineers." When Schroeder was repatriated in a prisoner exchange, he reported this conversation. The implication was obvious. Composite armor was an American innovation, not shared with Britain. That meant limited production capacity and specific manufacturing requirements. German intelligence redoubled their efforts to acquire intact samples and understand the production process. The race was on. October 14, 1943. The second raid. 300 B-17s flew toward Schweinfurt that morning, carrying the war deep into Germany's industrial heart. The ball bearing factories there supplied 60% of Germany's war machine. Destroy them, and panzers would stop rolling within months. But the Luftwaffe knew this. Over 300 fighters rose to meet the bomber stream. The resulting battle became the bloodiest day in American aviation history. By mission's end, 60 B-17s were destroyed. 600 American airmen were dead, wounded, or captured. But among the wreckage, a strange pattern emerged. Bombers with catastrophic damage to their fuselages and wings limped home. Their crews survived because composite armor protected their positions even as the aircraft disintegrated around them. One B-17, named Jersey Bounce, took cannon fire that severed the entire tail section. The bomber went into a flat spin, yet 5 crew members survived because the cockpit armor held. They parachuted into Germany and spent the rest of the war as prisoners, but they were alive. The pilot, Lieutenant Robert Johnson, wrote in his post-capture debriefing, "I felt the shell hit right behind my seat. Heard the bang. Felt the heat. But nothing came through. That armor saved my life." German pilots noticed too. Hauptmann Egon Mayer, a veteran fighter ace, reported, "We hit them hard. Shells that should penetrate don't. Their armor works differently than ours. It flexes, absorbs, dissipates. Our cannon shells mushroom against it." The Schweinfurt raid proved 2 things. First, daylight bombing deep into Germany was prohibitively costly without fighter escort. Second, American armor technology was keeping casualty rates lower than they should have been. For every 10 B-17s shot down, 7 would have been lost if not for composite armor protection. That margin meant thousands of American lives saved, and thousands more German fighters expended trying to achieve kills. Professor Vollmer faced an impossible task. He understood what the material was, fabric and resin composite. He understood how it worked, layered energy dissipation. What he couldn't figure out was how to manufacture it at scale. German industry was already straining under Allied bombing. Synthetic resin production was prioritized for aircraft and submarine construction. Cotton fabric was in short supply, diverted to military uniforms and medical supplies. Worse, the specific manufacturing process proved elusive. Vollmer's team tried dozens of resin formulations, pressing temperatures, and fabric weaves. Every attempt produced armor inferior to the American version. Too brittle, too heavy, too expensive. One sample shattered during cold weather testing. Another delaminate when exposed to aviation fuel vapors. The Americans had optimized their process through years of trial and error. Germany didn't have years. "We need the actual production specifications," Vollmer told Milch during a tense briefing in January 1944. "Without them, we're guessing. Our best reproduction weighs 40% more than the American version and stops 20% fewer projectiles." Milch's response was cold. "Then steal them. I don't care how. The Führer has ordered that we match American armor production by summer. Make it happen." German intelligence launched Operation Doppelganger, an effort to infiltrate American aircraft plants and steal manufacturing specifications. 2 agents were inserted into Boeing's Seattle facility through a complex network of sympathizers. Neither survived long enough to transmit useful information. American counterintelligence, warned by decrypted German communications, was waiting. Meanwhile, German industry pursued an alternate path. If they couldn't copy American composite armor, they would develop something better. The Luftwaffe commissioned ceramic metal hybrid armor that theoretically offered superior protection at comparable weight. Prototype tests were promising. Production tests were disastrous. The ceramic components cracked during installation, shattered under vibration stress, and proved impossible to manufacture consistently with Germany's degraded industrial capacity. By mid-1944, the effort was abandoned. Germany would never match American armor technology. The armor's success was measured in lives saved, but those statistics hid grim realities. Composite armor protected against fragments and smaller caliber rounds, but it wasn't invincible. German 30mm cannon shells still punched through. Direct hits from 88mm flak shells vaporized entire sections of fuselage, armor and all. For every crew member saved by the armor, another died because the protection wasn't quite enough. Tech Sergeant Michael Romano survived 3 tours over Germany. His B-17, made in America, took over 800 holes from flak and fighter attacks. The composite armor behind his waist gun position stopped 11 shell fragments that would have killed him. But during his final mission, a 20mm shell penetrated the armor at an oblique angle, striking him in the shoulder. He bled out over the North Sea before his crew could land. His last words, recorded by the flight engineer, were, "Tell them the armor worked. Tell them I'm only dying because I leaned wrong." Romano's story repeated thousands of times. The armor was revolutionary, but war is chaos. Projectiles struck from unexpected angles. Explosions overwhelmed any protection. Fire cooked crew members alive in their armor-protected positions. The psychological impact was subtle but real. Men trusted the armor, sometimes too much, staying at their positions when they should have bailed out. American commanders struggled with the moral arithmetic. Composite armor increased survival rates by approximately 30% in crew positions. That meant roughly 5,000 airmen who would have died instead survived. But should they have been sent on those missions at all? The armor made certain tactics feasible that would have been suicide otherwise. Did better protection justify more dangerous missions? The debate raged in planning rooms and congressional hearings for years after the war. But in 1944, the answer was simple. The armor worked well enough, and the war demanded maximum effort. Men would fly. Men would die. The armor would save some of them. It would have to be enough. By early 1945, American engineers had refined composite armor to its theoretical limits. The B-29 Superfortress, designed for the Pacific Theater, incorporated lessons learned from 3 years of B-17 combat. Armor panels were contoured to aircraft shapes, reducing weight while improving coverage. New resin formulations increased heat resistance for the high-altitude, pressurized environment. Some panels incorporated thin aluminum face sheets, creating a hybrid armor that combined composite energy absorption with metal's projectile-deflecting properties. German engineers, meanwhile, had given up on copying the technology. Instead, they focused on defeating it. New cannon ammunition types were developed specifically to penetrate layered armor. Tungsten core projectiles could punch through 8 inches of composite material. High-explosive incendiary rounds created secondary effects that overwhelmed the armor's protective capacity through blast and fire rather than penetration. The technological race had reached its inevitable conclusion. Any armor could be defeated with sufficient firepower. Any firepower could be countered with sufficient armor. But weight, cost, and manufacturing capacity set hard limits. The Americans had reached the optimal balance between protection and practicality. The Germans had reached the limits of their industrial capability. In April 1945, Vollmer sat in his laboratory, examining one final composite armor sample recovered from a B-17 shot down near Berlin. The bomber had been hit by 3 88mm shells. 2 penetrated. 1 didn't. The crew died anyway when fire consumed the aircraft. Vollmer carefully labeled the sample, "Final Analysis. Project Terminated." The war in Europe ended 3 weeks later. In the rubble of German research facilities, American technical intelligence teams found Vollmer's reports. They were impressed by how close German scientists had come to replicating the composite armor, and relieved by how far they'd remained from success. The true margin of victory, they realized, wasn't just better engineering. It was having the industrial capacity to implement that engineering at scale, something Germany never possessed. The B-17 composite armor disappeared from public consciousness after the war, classified and forgotten as aviation technology leaped into the jet age. But the principle survived. Modern body armor, Kevlar vests worn by soldiers and police, uses the same layered composite approach developed for the Flying Fortress. Aramid fibers replaced cotton, advanced polymers replaced phenolic resin, but the core concept remained identical. Dissipate impact energy across multiple layers, each one contributing to the whole. In 1952, DuPont chemist Stephanie Kwolek began research into synthetic fibers for aircraft tires. Her work led to Kevlar, commercialized in 1965. Military applications followed immediately. By Vietnam, American helicopter crews wore composite armor vests. By 1975, police departments issued Kevlar body armor to officers. By 1990, composite armor protected vehicles, aircraft, and ships worldwide. The B-17's armor panels, once so mysterious to German engineers, had become the foundation of modern personal protection. Oberfeldwebel Klaus Richter survived the war and became an aviation mechanic for Lufthansa. In 1978, a journalist interviewed him about his wartime experiences. The reporter asked if anything surprised him about American technology. Richter didn't hesitate. "Their armor. We thought they had some miracle material, some secret weapon. Turned out it was cotton and glue, pressed together by clever men who understood that sometimes simple solutions are the best solutions." He paused, looking at a photograph of a B-17 hanging on his workshop wall. "We were trying to win through complexity, through superior individual engineering. They won through pragmatism and production capacity. The armor was just a symbol of that larger truth. They could afford to protect their men with revolutionary materials manufactured by the ton. We couldn't even copy it with all our technical expertise." The B-17 composite armor saved an estimated 8,000 American lives during the war. That's 8,000 men who returned home, raised families, built careers, and shaped the post-war world. The material that German mechanics never quite understood became one of World War II's quiet game-changers, not dramatic enough for headlines, but profound enough to alter the course of thousands of individual lives. In a storage facility in Dayton, Ohio, one original composite armor panel from a B-17 remains on display. Visitors rarely notice it. It looks unremarkable. Just layers of fabric, pressed and bound, discolored with age. But touch it, and you can still feel the indentation where a 20mm shell struck 78 years ago. Feel it, and remember that sometimes the most important innovations aren't the loudest ones. Sometimes they're the ones that simply bring people home alive.